So this is second lecture of properties of Laplace transform, and we're going to see some very important properties right now. So firstly, suppose the Laplace transform of x of t is x of s, and we want to find out what's the Laplace transform of dx of dt. So we're going to find out the Laplace transform of dx of dt right now. According to our definition, it's going to be 0 to infinity dx by dt e to the power minus st dt, and it's begging for integration by parts, so I'm going to do it by di method. Alright, now which one to differentiate? Alright, so if we differentiate this, we are not going to come back to x, which we want to relate with. So this should have been integrated, this should be integrated, and this should be differentiated. Alright, after first step we get e to the power minus st minus s and x on here. So after first step our result should be e to the power minus st x to be evaluated from 0 to infinity, and then a minus cancels out, so plus s 0 to infinity x e to the power minus st dt. Again I am saying, those who are not familiar with the di method, search it on Google. Alright, now e to the power minus infinity is always 0, so e to the power 0 can be applied. E to the power 0 is 1, so what left is minus x of 0 plus s, and this is the Laplace transform of x of s. Alright, so we see that dx by dt shares the Laplace transform of x of s minus x of 0. If we continue the hierarchy, we will see that the Laplace transform of d to the power x minus dt square is equals to simply s square x of s minus s x of 0 minus x dash of 0. Alright, it's the first derivative of x, and the continuation is that if we are continuing with mth derivative, then there is going to be first of all sm x of s, and then there is going to be x of 0 term, x dash of 0 term, like this till xm of 0 term, and the coefficient with x of 0 term is going to be s of m minus 1. The coefficient with x dash of 0 term is going to be s of m minus 1 till here on, and all the terms are going to have negative signs. Alright, so that's the hierarchy of what happens if we differentiate again and again on time domain. Remember that s to the power m, the time you differentiate it on x domain, you multiply that times s on the Laplace domain plus some additive factor depending on your initial conditions. Alright, and there is x of 0, x dash of 0, and all the initial conditions of derivatives and values, and s gets multiplied there on. Alright, so we're going to see some application of this property right now. It has been asked to find out the inverse Laplace transform of s plus 3. Alright, so s plus 3, we want to find its inverse Laplace transform, so L inverse. According to our linearity property, it's equals to L inverse s, L inverse 3. Now L inverse 3 is very easy, it's going to be 3 and L inverse 1, and we know the Laplace transform of 1 is delta t. But what is going to happen about L inverse s? L inverse s is s times 1, so it was actually the Laplace inverse Laplace of 1, then somebody multiplied the s, and what happens if s is multiplied in your s domain, then you have to differentiate it on your time domain, right? The inverse Laplace of 1 was delta t, but as s is multiplied, you have to differentiate this, so delta dash t plus inverse Laplace of 1 is simply delta t. So this is our inverse Laplace transform. You see, it's very useful. Now what happens when you integrate on time domain? Alright, so the xt has time is domain picture of x of s, and we want to know when the integrator is applied to xt, what is the picture on s domain. Alright, so let's solve it from our definition. It's going to be 0 to infinity 0 to t x of t dt times e to the power minus st dt. Now again begging for integration by parts, and I'm going to solve it by di method. Alright, now which is the function should I differentiate? If you integrate this, you're going to get second integral. but if we differentiate it, we will get xt, and then we can relate it with x of s, which is our main target. So x of t dt and integral is e to the power minus st. After our first differentiation and integration, we get x of t here and e to the power minus st by minus s here. So first term to evaluate is going to be minus 1 by s x of t dt integration from 0 to t e to the power minus st to be evaluated from 0 to infinity. Alright, and another minus term, so minus minus gets cancelled out, plus the integral, next integral is going to be x of t e to the power minus st 1 by s dt. Alright, now when you put infinity here, e to the power minus infinity is 0, so that's going to be 0, but when you put 0 here, it's going to be 1, and here is going to be x of 0. Alright, plus 1 by s, and this is simply the Laplace transform of xt. So it's going to be x of s, and if we assume, which is mostly for our real functions true, that the initial value of function is 0, then it's going to be 1 by s x of s. Remember, it holds only when the initial value of our function is 0. Alright, so we're going to see some application of integration in time domain. But let me tell you one more thing. When you integrate once, you get 1 by s. When you integrate twice, you will get 1 by s square. So integration in time domain means dividing by s in s domain, in Laplace domain. Alright. So you see, I'll tell you later more when I show how to solve differential equation by Laplace. But you see the picture that the operations like differentiation, integration are becoming algebraic operations in Laplace domain. So it is asked to find out the Laplace transform of r of t. We really don't know how to find out the Laplace transform of ramp of t. Obviously it's t ut, you can do it in that way, but for application purpose I'm going to assume it. Ramp of t is simply the integral of unit step function. Alright, and we know that the Laplace transform of unit step is 1 by s. Now as ramp is an integral, it is going to be divided by 1 more s. So the Laplace transform of ramp of t is going to be 1 over s square. So very handy property. Now we will see what happens when you differentiate in your time domain really. Alright. When you differentiate in the s domain, in Laplace domain. So the inverse Laplace transform of x of s is simply x of t, and the inverse, we want to know what's the inverse Laplace transform of dx by ds. So what is x of s? Alright, it's going to be 0 to infinity x of t e to the power st and dt. Alright, e to the power minus st dt. Then what's going to be dx over ds? Dx over ds is going to be d by ds 0 to infinity x of t e to the power minus st dt, and by Leibniz we can take the difference derivative under integral sign, but we need to make it partial derivative. Alright, so 0 to infinity delta over delta s x of t e to the power minus st times dt, and the differentiation will result as it is with respect to s, so it's going to be e to the power minus st and a minus t here times dt, and this is going to be simply equals to the minus, if we take the minus out, and then if we rearrange the term tx of t e to the power minus st dt, then you see that it's simply the Laplace transform of tx of t with a negative sign. So what does it says? That it says if x of t is simply x of s, then dx by ds is going to be minus tx of t, and if we continue the hierarchy, then you will see d square x by ds square is going to be t square x of t minus 1 square, simply minus 1 here, and the ultimate result is that suppose you can see it from both ways. Suppose you multiply in the by t in the time domain, instead of thinking that to differentiate in the s domain, you think in this way, you multiply by t in the s domain, t to the power n x of t. Then the s domain picture is going to be dx d to the power n x over dsn, but a minus 1 to the power n. Alright, if you differentiate on s domain, you get multiply by t on the x domain, t to time domain. Alright, but on the vice versa, if you multiply by t on time domain, you have to take derivative in the s domain. So really it's beautiful, and it's one of the most important property in inverse Laplace transform. So it has been asked to find out the inverse Laplace transform of 1 by s plus a square, right? But try to see, we know the inverse Laplace transform of 1 by s plus a. What's the inverse Laplace transform of 1 by s plus a? E to the power minus at ut, right? And what is 1 by s plus a square? 1 by s plus a square is simply minus our derivative of 1 by s plus a, right? Because derivative of 1 by s plus a would be minus of 1 by s plus a square, then a minus would cancel out it. Alright, the minus will cancel out the minus. So we know the Laplace transform of 1 by s plus a, then as it is derivative in the s domain, it should be multiplied by t in the t domain, and the minus sign should hold on, because homogeneity holds in Laplace transform, and this will be our inverse Laplace transform. So when you see functions like 1 by s plus a to the power n, you need to find out the inverse Laplace transform by thinking of it as the derivative, nth derivative of 1 by s plus a times some multiplying factor. Alright, this will hold. This is a very good trick in inverse Laplace transform. Now the next thing we want to talk about is the modulation. Modulation, what is modulation? Modulation happens when you want to change frequency, and when you want to change the frequency of your signal. But right now we are thinking about the s domain, not Fourier domain. So we want to know that if we multiply a signal by cosine of omega naught t, what happens in our s domain? What are the effect in our Laplace domain? Alright, so x of t cosine of omega naught t by Laplace by Euler can be said like this. So it's going to be half of x of t e to the power j omega naught t plus e to the power minus j omega naught t, and then if we multiply it, factorize it, plus x of t e to the power minus j omega naught t. Now as we know our properties, we know the property from first lecture, that if x of t is x of s, then x of t e to the power minus s naught t is going to be plus s naught t is going to be x of s minus s naught, right? So there is an exponential factor, exponential time factor, so there is going to be a shift in the s domain, and the shifting sign is going to be opposite of the exponential factor. So the Laplace transformation is going to be half of x of s minus j omega plus x of s plus j omega. So when you add, when you multiply by cosine omega t, you have the same wave shape, but one transformed, one delayed, and one had came earlier in the time in the s domain. Alright, so what happens when you multiply by sine of omega naught t? Very simple picture. It's going to be half of x of t e to the power j omega naught t 1 by 2j before, minus e to the power minus j omega naught t. So if we factorize it, it's going to be x of t e to the power j omega naught t minus x of t e to the power minus j omega naught t, exponential time factor. So that means shifting in the s domain 1 by 2j. So the Laplace transform is going to be 1 by 2j x of s minus j omega naught minus x of s plus j omega naught. So that's all for modulation. You see, when modulated, suppose if this was our x of s, then multiplying by cosine omega naught t is going to produce some s domain picture like this, a shifted version, that frequency in the s domain You can think of this as the frequency being changed and shifted. Modulation does that, right? We know modulation modulates our frequency. Now, the last thing for in this video which I want to discuss in this video is convolution. Now, I will not derive it. The derivation has been so cliche and so common. So, when you convolute in the time domain, actually your S-domain picture becomes a simple multiplication, right? So if you take the Laplace transform of this signal and this signal, the signals which you want to convolute, and then multiply them, then you find out the Laplace transform of your wanted signal, which was the output or result, and then you can take the inverse Laplace transform and find out y of t, which we are going to do now in an example. Alright, so it has been asked to convolute to rectangular function, and we know we have seen before in this video or the past video, rectangular t minus a by twice a is going to be u of t minus twice a. So its Laplace transform is going to be 1 by s divided by 1 by s e to the power minus twice a s, right? Because a time shifted factor, time has been shifted, so there is going to be exponential with the same sign. So when I try to convolute, let's call the result yt has been equal to this convolution. So then y of s, the S domain picture of our output signal, is going to be 1 minus e to the power minus twice a s over s, and simply multiplication again. If we multiply, we are going to get 1 minus s square here, then 1 minus e to the power minus twice as whole square, and if we evaluate it, then we are going to get 1 minus twice e to the power minus twice s plus e to the power minus 4s over s square. If we make the numerator side by side, then we are going to get minus twice e to the power minus twice s over s square plus 1 by s square e to the power minus 4as. We really, to inverse Laplace transform, we should first think about the portion without the exponential, because the exponential is really a time shift. Alright, so what's the Laplace transform of 1 by s square? It's going to be t, u of t, right? We have seen the Laplace transform of t to the power n in our, I think, one video before. You can review that the Laplace transform of t to the power n was simply n factorial over s to the power n plus 1, and if you replace t to the power 1 here, then you are going to get 1 by s square. So the inverse Laplace transform of 1 by s square is t u of t, then minus 2 by s square, so it seems like 2t u of t, but there is an exponential factor of e to the power minus twice as, so there is a time shift of same sign as the exponential factor. So this signal, this portion is handled out, and 1 by s square, again this is simply t u to the power t, the basic signal, but a shift of minus 4a, so t minus 4a u of t minus 4a. So thank you. Now 5 properties has been covered here. There are 3 to 4 more properties which I'll cover in the next video, the last video of properties.